Alrighty, back for day 4. If you are just jumping in at this stage of the video, we're walking through my solutions for Advent of Code 2023. Hey, I'm Elliot and I build stuff. All right, let's go. So day 4 was all about scratch cards. If we scroll down to the input file here, you can see that we get a collection of lines, each of which has 1, 2, 3, 4, up to 5, exactly 5 numbers on the left of this pipe, and then 8 numbers to the right. And the way this input is set up, you've got the numbers that we guessed here. It's kind of like a lottery, and then these were the winning numbers. And for part 1, we needed to calculate a score. And the score was based on the number of matches. The first match gave you 1 point. The second match doubled your score and gave you 2. The third match doubled your score again and gave you 4, and so on and so on. So we needed to read in each of these cards, find the number of matches in any given card, and then calculate the score, which turned out to be 2 to the power of matches minus 1, which we'll see when we jump into the code. But then sum all the scores together for all the different cards, and then report that back as the total. So if we do that, we've got 22897. So let's have a look at that one. Getting pretty simple to begin with. So here's the code as always, reading in the text file into a big string. And then we jump through, keep a running total of the score. We store a vector of card matches, which is really more about part 2, which we'll get to later. We then read it line by splitting on the new line characters. We skip any empty lines. Sometimes when I was copying and pasting, I added an extra line to the end. This just dealt with that. So we split the line at the colon. So if we go back here and have a look, we've got card space card number colon. So we split there. The card information, which we kind of just discard, is the first part of that. And then the actual information about the game becomes the second part. We then split it again at the pipe character, and we take the numbers to the left and we take the numbers to the right. So what we've got now is we've got 2 strings, which represent the winning numbers and the list of numbers that we've guessed. I actually got that round the wrong way last time. The numbers to the left are the winning numbers, and then to the right is the number that you guessed. But it's all the same, really. We just store those 2. We then take those winning numbers and we store them in a binary tree set. This was a little overkill, to be honest, given that there's a red hot 8 numbers in there. But we do it anyway because it has a really fast lookup time. So the way that Advent of Code works, for those unfamiliar, is you don't get part 2 revealed until you finish part 1. I had a suspicion that part 2 was going to be slightly different than it ended up being. And this is probably a case of sort of prematurely optimizing this, given that there was only ever 5 numbers we needed to look up. We could have easily used a much simpler data structure here, but nonetheless, we take the winning numbers, we split them based on white spaces, parse each number into a 32-bit unsigned integer, and stick it in the binary tree. To then find the matches, we split the right-hand side, we parse the value as a 32-bit unsigned integer, check our set, see if it contained the value that we guessed, and if it did, we add 1 to the matches. For part 2, we store the matches in a file, in a vector. So we store for each card the number of matching numbers, and we'll see why later. But for part 1, the main thing was if there's more than 0 matches, the score gets incremented by 2 to the power of matches minus 1, as we talked about before. So skipping all of this code for part 2, we then print out the total number of the score, and that's the end. So let's dive into part 2. This is where things start to get a little bit more interesting, I think, for the first time in Advent of Code this year. The points, as it turns out, are completely made up and mean nothing. It turns out that the actual rules of the game are that if you win a scratch card, you win more scratch cards, which is a very strange game to play. Hopefully it doesn't cost you any money. But if you win on scratch card 1 and you have one match, you win a free copy of scratch card 2, and so on and so on. So if you win, if you have 5 matches, you win one additional copy of the next 5 scratch cards. And what they want us to do now is say, okay, if we start at the top of our list, we play this scratch card, card 1, collect any new winning scratch cards, go through and play card 2, 3, 4, 5, and play all of the cards that we win along the way, knowing that in the cards that you win, you can then subsequently win more cards. How many cards will we play in total? And this number can get big pretty quickly. They walk through an example here where in card 1, you have 4 matches, so you win a copy of cards 2, 3, 4, and 5. Your original card 2 has 2 matches, so you win a copy of card 3 and 4. So now we've got 2 copies of card 3 and 2 copies of card 4. But then the card that we won, the duplicate of card 2, also wins another 3 and another 4. And you can see how these numbers can stack up to be quite large. So this is probably the first point where you can spot a flag that doing this by just running through each of the games and playing them might not be the approach they're looking for you to take here. What ends up being a more efficient way of running through this is to use a technique known as dynamic programming. And dynamic programming is a big, scary-sounding word, which basically means using memory and storing some results to avoid recomputing results later, for lack of a better term. Or this particular type of dynamic programming is certainly doing that. And the things to look out for that might hint towards a dynamic programming solution is when you need to do some computation, let's say calculate the number of matching numbers a whole bunch of times. So we might need to compute how many times card 3 matches, 2, 3 times based on whether card 1 and 2 are winners. And you can see here in this particular walkthrough, you get 8 copies of card 5. Once we know how many times card 5 matches, if we can just store that and look it up, that saves us having to compute that over and over and over again, and it makes things much faster. Another rule that I'll note here is that if you win on, say, card 6, because there are no further cards in the list, you just get nothing extra. So there's a nice stopping condition here at card 6, which says, okay, if we hit the end of the list, nothing else needs to be done. So the insight for this problem is really the understanding, you can do it the brute force way. By the way, the final number is 5095824, so about 5 million cards. The time to do, up to 5 potential matches, it's not going to be huge. You really probably could have brute forced this one, but from a most efficient way to do things, certainly dynamic programming has an advantage here. So the way that we tackle this problem, or that I tackled this problem at the very least, is by working from the bottom of the list up. Now, the reason we started at the bottom is because we know that if you hit the bottom and you win something, there's nothing further that you can win. So, for example, in card 6, even if there were 5 matches, you get no additional cards. So let's jump back to the code and have a look at what we did here. So you'll note in our walkthrough of part 1, whenever we got a match, we were actually storing the number of matches in this card matches. I think it's a vector. It might be a set. No, it's just a vector. So we stored in there the number of matches working from the top. So by the time we finish this first loop, for every card in our original set of cards, we have the number of matches that that card has stored away somewhere. So now for part 2, we reverse the list, so it goes bottom to top, and we start at that very bottom, and we calculate the number of matches, and then we store that number of matches plus the number of matches of any additional cards that we win. Now, because we start at the bottom and we're working up, by the time, let's say, jumping back here, by the time we look for matches in card 5, the only possible card that we could win there is card 6. We already know how many additional cards card 6 generates, so we don't have to go through that loop again. We can just grab that number and add it to our total. Similar with 4. Let's say, for example, 4 had 2 matches. We'd win a 5 and we'd win a 6. We already know how many additional cards 5 generates and 6 generates. We don't actually have to run through them. We can just take that total and add it to the total number of cards won by card 4. And that's exactly what we did here. So we ran through a reversed version of that list of matching numbers from before. We enumerated through it so we could store the offset as well as the value. And we jumped through. So one of the things that we did is we did a little check here and said, look, we know the number of matches that the card that we're up to has. Let's find the number of matches in all of the cards beyond that and add them to our list. Now, we did a couple of checks here to make sure we didn't run off the end of the list. But really, all we're doing is saying, okay, we have 3 matches, so look up the next or the previous 3 stored values and add them to our total. We proceed to do this for all of the matches, and then we store the match for that current card. Now, this might be a little bit complex, so I'm going to run through this back in the browser window to give you a bit of an explanation. So for card 6, I'm pretty sure, card 6 doesn't actually have any matches. So we know that card 6 generates 0 additional matches. So the first entry in our running matches vector our running matches vector is the number 0. Card 5, it doesn't have any matches either, so it generates no additional cards, so we'd store 0 there as well. Card 4, in this case, it has 1 matching number, so we win some number of copies of card 5, but card 5 generates 0 additional matches, so we win 1 card from number 4 and nothing additional from the additional copy of card 5 that we won. Sorry. And so that's represented here. We come through, we match the cards, we start at whatever number we're up to, we loop through, incrementing this counter C each time until we've gone through the matches, and looking up whatever number of cards it was in our previous storage area. Doing this, running this all the way through, we get the number of cards that we generate for each card in the list. So we've got a list here now running matches, which is as long as the input file in terms of cards. We loop through that, we sum them all together, and then we report that as the total by also adding the number of cards in the original list. So we don't bother storing the 1 card that we get as part of the original game. Running matches just stores how many additional cards we win along the way. So by doing that, as we said before, we end up with 5095824, and that's our second gold star for day 4. So you can see there that one is a little bit more complex. using a sort of dynamic programming solution there. But once you spot that as a potential solution, storing values, looping through, doing lookups, it's actually quite a simple solution. You know, we're talking about here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines of code to actually loop through and look those numbers up, which avoids us having to, keep let's say a running list of cards to process or anything like that. And given that there's 5 million cards at the end of the day, this is a much more efficient way to do this. And if this would have, let's say they gave us a list with 1 million cards in it, those numbers could get quite massive. And this solution really only requires us to parse through and keep track of the number of matches once, and then work backwards through the list, storing the running total. The inner loop here is quite small. The largest this could ever be is 5 if we've got 5 matches. So it keeps the computational complexity of this problem pretty well contained. So hopefully that was helpful. Starting to get a little bit more complex here with day 4. But I'm Elliot. I build stuff, and I'll catch you at the next one.